let me recap a bit. So I realized that I might be a bit too fast on last Friday on how to compute expanded decomposition fast. So for today, we're just gonna assume that as a black box. So if you didn't really understand that, it's okay. We're just gonna assume that and then use it to build the BSE hierarchy fast. But if we have time, I'm just gonna recap how to do expanded decomposition fast again. Yeah, okay. So let's again recap about what's going on in the whole course so far, right? There are two primitives. One is expanded decomposition, one is expanding balance separator. Okay. For the expanded decomposition, there are some variant of it. The strengthening of it, which is the Butterly link version and the dynamic version. Okay. So now, in your homework, you will basically show that the cut matching game with deletion. Okay. The cut matching with deletion give you. How can I? What? I cannot draw. 1 second. Let me restart. Okay, 1 second. So, okay, from the cut matching game, you can get this subroutine that either return balanced sparse cut or return a giant expanding set. And from this subroutine, we showed last time how to get expanded decomposition. Okay, so that's like from previous class. Okay. Also, we see that the cut matching game with deletion and transferring vector, you can also use it to build this one. Okay. Well, there is like a cut matching game, the standard version, without deletion and without transfer. Do you recall like what did we use? We showed this one application of this guy in class. What's that again? What did we use this thing for? Yeah.
Like to compute like either a sparse cut or an expander.
Yeah. To just check if there is some, like, to say that there is a phi sparse cut, or just to say that the whole graph is phi over log square expanding, or the whole node weighting is phi over log square expanding. Okay, so this is like kind of just to find like approximate sparsest cut. So if you have this algorithm, you can use it to build this thing and to build this thing, but it will not be fast, right? Because the algorithm to build, like if you use an algorithm to find sparsest cut, approximate sparsest cut as a black box, you might need to call it many times because the cut might be not balanced. So like, right? But we basically, so this subroutine is kind of good, but it's just not strong enough to build fast algorithm for both of these guys. That's why we kind of want the more advanced version of cut matching game to just build these two fast directly. Okay. But all of these things now, we can build it in basically polylog mac flows. And after that, if you can build expanded decomposition in polylog mac flow, you should be convinced that we can build this thing, repeated expanded decomposition in polylog mac flow too, because we really just compute expanded decomposition and recurse on the cut edges and repeat this log n times. So this is fast too. Okay. How can we build this thing fast too? Anyone recall? What is SE hierarchy and how we can build it fast? Yeah,
just
Michael.
Lines of expanding and separator.
Yeah, right. Just keep like applying expanding balance separator to get basically the separator in the top level, and then recurse on each component. The recursion depth will be log n. So if this is fast, then this is going to be fast too. Okay. But we learned like that there is like a stronger version of SE hierarchy, which is BSE hierarchy, which is like, it's a kind of similar hierarchy, but it's not just separator that is expanding. It's a boundary that is expanding too. Okay. However, like the straightforward algorithm to build SE hierarchy from expanding balance separator, it just gives you this thing. It doesn't give you this thing. So we don't have a fast algorithm for this one yet. Okay. So, but we learn how to build BSE hierarchy in some way, which is based on the dynamic version of expanded decomposition. Okay. But we don't actually have fast algorithm for this one yet. Also, even if you assume fast algorithm for this one, we don't have fast algorithm here. So this is not fast yet. Okay. So that's the today's topic. We're gonna basically build BSE hierarchy fast. Yeah. That's today. But you see that like the quality of the BSE hierarchy from today is not ideal. The ideal one should be of quality like polylog, but we're gonna get something worse. Okay, you see that we get something worse, and it's actually open how to build it. How to build this one fast with polylog quality. So after today, that's the open problem that you can think about. And right, from all this kind of key hierarchy and decomposition, like you should try to convince yourself that the edge specifier that we learned from class now, you can do it fast. Vertex specifier, you can do it fast too, because even the bodily link version of expanded decomposition, you can do it fast. We assume it today, and if we have time, I sketch how to do it. Yeah. So this is fast. This is fast. This one is fast too. So this one is going to be fast, assuming that this is fast. This one, I didn't talk about it yet. Like we will talk about it when we start to talk about fast algorithm for flow. Yeah. Yeah. But basically, we kind of at the stage where all the technology that we have seen so far that we built, now most of them are now fast, yeah, except this one. So that's today. Okay. Questions about the goal? And yeah. Good. All right. So let me recall BSE hierarchy, right? So the 5 bodily separator expanding hierarchy. So 5 BSE hierarchy. Right? This is just a hierarchy of a graph. It's a hierarchy of a graph, which is, the kind of laminar family of induced subgraph. And what we have is that for every cluster, every induced subgraph in the hierarchy, we have that its boundary and its separator is expanding inside the cluster H. For example, in the root cluster, which is the whole graph G, there is no boundary, so it's just said that the separator of G is expanding in G. But the children cluster, which is after you separate this thing, you get the children here, right? Then this is H2. Then we have that both of the boundary of H and the separator of H, the green one here, is expanding in H2. Like actually 5 expanding. Yeah. So which means that any demand that respect the boundary or the separator, you can route it with low congestion. So this is just to recap the definition. Any question about you recall this thing, right? Yeah. Okay. So the goal today is that we can, given any graph, I'm gonna build this thing. 1 over n to the little 1. You see exactly what is n to the little 1 soon, but it's something that is worse than 1 over polylog. This is worse than this thing, but still better than 1 over n to the epsilon, right? It's better than any polynomial, but it's worse than polylog. Yeah. So we're gonna build this with this expansion, okay? And there will be just square root log n levels. Okay? But if you recall, once you have this BSE hierarchy, we can get the tree flow specifier, which is a really strong object. Yeah, it's like a tree that's approximate the whole graph with this quality. And the algorithm is going to be quite simple. We're just going to call boundary linked expanded decomposition square root log n times. It's going to be really simple. You're going to see it soon. Yeah. Okay. So it's really going to be really fast, but the quality is n to the little 1. Quite good, but not ideal. So let's recall boundary link expanded decomposition a bit. Okay. So it's this one, right? Where you have a graph, you have a node weighting, and then you have some kind of boundary linked parameter beta, which shouldn't be too big compared to 1 over 5. It's like something like 1 over 4 log 5. 1 over 5 times 1 over log, basically. That's how you think about it. Okay. So it's just some parameter. And then we said that we saw before that the x is a cut such that the cut size not too big. Okay? The cut size is like a 5 fraction of A. But then after cutting this cut from the graph, after cutting C from the graph, then A, the node weighting, plus the boundary of a cut. Right? This is like the boundary of a cut. A plus the boundary of the cut even scale up by beta. So you think of beta as something big, but not too big compared to 1/5. It's like, even when you scale up by beta, which is much more than 1, right? Can be much more than 1. This is going to be phi expanding. So in picture, when you remove the cut, C, and then you look at each component here, right? The node weighting A, even together with the boundary, when the boundary scale up by factor out beta, this boundary together with A is expanding in the component. Okay. All right. So this we saw. Okay. And using basically the same algorithm from Friday, we can build it fast too. Okay. So what do we have here? Basically, it's the same, except that instead of having that, this guy is phi expanding. It's going to be a bit worse than phi. It's going to be, let's say, call it phi prime, okay, which is a bit worse than phi, something like phi over log square. Okay. And the running time is basically the same, like expanded decomposition. So on Friday, we show this one, where like there's no boundary link term, but here I just claim that you can just add this for free. Okay. And just recall, like Tm here is like the time to phi max flow, so you just need polylog minimax flow calls. And yeah, if we have time, we're gonna recap how to do this again. Yeah. How to compute this. But for now, let's assume this. Okay. Let's assume that we can build boundary linked expanded decomposition fast, like polylog max flow. Okay. Okay. And the way that you should think for this lecture, we will set A here to be just the node weighting of the whole graph, the degree of G. Okay. And you should think of phi here as something weird like this, which is 1/log to the power of root log n. Okay. So this is the one which look like 1/n to the little 1. Okay. So it's smaller than 1/polylog, but larger than 1/n to the epsilon. And beta, you just set it to be maximum as you can. Okay. That's how we're gonna use it in today's lecture. So it means that if you look at each component, then you have this part, which is like basically A intersect U, which is this thing. This thing is going to be phi prime expanding. Okay. But the boundary here, the boundary is going to be phi prime over beta expanding. Because you know that the boundary, like beta times the boundary is phi prime expanding. So it means that the boundary is phi prime over beta expanding. Wait, is it? No. It should be beta times this thing, right? Yeah. Sorry. Yeah. Yeah, even if you scale up, like when you scale up the battery by beta is phi prime expanding. So if you look at this thing only, then it's going to be beta phi prime expanding. Okay. And what's beta phi prime? This looks like 1 over log cube, right? Because phi prime, yeah. Phi prime is like phi over log square, and beta is like a 1 over, yeah. Phi prime beta is like phi over log square, and beta is like 1 over phi times 1 over log. So this is like log cube. Okay. Okay. So my point is that the way you think about this is that the battery is much more expanding than the node weighting, like than the degree node weighting. Like the degree node weighting is just like 1 over n to the little one expanding, but the battery is 1 over log cube expanding. Right? This is like the message here is something that you need to understand. Are we good? If there is some part where the notation doesn't make sense, just ask, all right? Yeah. Okay. Good. All right. Okay. So we're just gonna assume that we can build this thing fast, where like we get this expanded decomposition, and once you cut it, then the battery here is really expanding well inside the component, and the degree node weighting. So that not just A here, but the degree node weighting, okay? Because we set A to be the whole thing. The degree node weighting is quite expanding, but not as good as the battery. Okay. Good. So now here's the algorithm. Okay. The algorithm is gonna be just like I said, just set phi and beta like I said. Okay. And let's say that the graph G naught is just G. And we're just gonna repeat like some loop. Okay. So what we're gonna do is we're gonna call the battery linked expanded decomposition on like CI. This is battery linked expanded decomposition on GI-1. Okay. So this is the one where like just the one from the last slide. Okay. This parameter phi and beta is just like in the last slide. And once you have this cut CI, then you look at the graph here after cutting CI, and you just contract each connected component in this graph. And let's say you remove all the self loop too. And that is your graph, GI. From GI minus 1, do battery link expanded decomposition, you get some component. For each component, contract that. Remove the self loop, that GI. Okay. And what you're gonna like, so you see that the graph keeps shrinking, and you're gonna stop when there's no edge. Okay. That's it. So Now the hierarchy will be just super nodes on all of the GI. So maybe I give you some picture. Okay. So suppose that I start with G0 like this. And then I get a cut. Maybe I cut it in this way. So that basically now, when I contract each component, this component is contracted. This component, there are 4 components here. So I just contract them. The self loop is removed. And now, like between these 2 guys, there are like two edges here. So you can draw parallel edges, or you can just draw an edge with capacity 2. Think of this as parallel edges, that's fine too. Okay? So this node now, I call it super node. Okay? This super node would correspond to the induced subgraph here. Okay. So that's like how you construct G1. And let's say that you compute expanded decomposition in G1, and if the cut is just empty, then it means that there is only one component, so you just contract it. So that's when there is no edge in this graph, because the whole component is just this thing. You contract it to this. So now this would correspond to the hierarchy like this, right? You have this super node here in G2. It's just the top level, the root cluster. And each of these point correspond to the cluster here, cluster here, cluster here. And the node in G0 just be a singleton in the hierarchy. Okay. Is it clear how we build this hierarchy? Just again, another illustration. You have G0, do Bartley linked expanded decomposition. You get a bunch of expanded cluster and the cut size here. Note that the cut is something like 5M. The cut size is like 5M because like your node weighting A is just degree of G. It's G0, right? And so the cut size here is like 5 times log n times this thing times log n. So it's like 5m. I ignore polylog here. And then G1 is just from contraction. And then we do, again, another Bartley link expanded decomposition. You may get this. This is like cluster, expanded cluster. And there are edges between the cluster. That's C2. And C2 will have size 5 square m, roughly. And then you contract it. You get this one, and repeat until you're done, until there's no edge. Just a quick question, if you understand this. Is it true that like at the last level, there's going to be just one node only? Is this always the case? Yes or no? Who think yes? Who think no? Why do you think yes? Lucas, yeah.
Not really my hand, but I feel like it always just contract down to one eventually. I mean, I don't have a very thorough explanation, but
right. So the picture looks like just always one node, but actually, there can be more than one. How can that be?
If the graph isn't originally connected.
Yeah, if the original graph is not connected. So that's the only reason. Yeah. But okay, we can assume that the graph is connected and there's going to be just one node at the end. Yeah. Okay.
So if the graph is connected, then there can only be one node at the end.
Yeah. Yeah. Okay. So now, so you see that the size of C I will be really just something like 2 phi log n to the I times m. This we won't have precisely, right? Because just the number of what's the number of edges in G2 in G1 is the number of edges in G1 is just the size of C1. The number of edges in G2 is the size of G2. So the cut size keeps shrinking by this factor. Okay. So now you, like, when is it the case that when is it the case that Ci is less than 1? For which value of Ci? Which value of I when this is less than 1? Like phi looks like log to the log n to the square root log n. Okay. So I claim that when I is at least root log n, when I is at least root log n, then this is less than 1. It's kind of just from how we choose this guy. Like that is like, because phi to the root log n, yeah, you're gonna get like times root log n here. But now it looks like, let's say that like, let's say that this is big. This big O here is like, this is like, I mean, anyway, like log n to the log n is less than 1 over n to the 100, right? This thing. So basically phi to the root log n is now like really small. Are we good? Is this calculation all right? Okay. So anyone want me to expand on this, or I can? Yeah?
What about the log n like after phi?
Right, because this log n is like so tiny compared to phi. So yeah, like let's see. 2 phi log n to the, let's say, root log n, right? Well, this is like, let's say that phi is 1 over log n to the, let's say, 10, let's say phi is just this. So this thing is then just, yeah, 2 log n over log n to the 10 root log n. Everything here to the log n, root log n. So this is kind of, you kind of just can ignore it now because it doesn't really matter anymore. Yeah, it's just like -1 here. Yeah, okay. And this is just 1 over log n to the 10 log n, something like that. So that's like much less than n to the 100. Okay. So even if you multiply this thing by m, which is at most n square, it's going to be still tiny, less than 1. Okay, so you see that just this algorithm, will be at most root log n levels. And the algorithm really just do binary link expanded decomposition for L many times. That's the whole algorithm. So if the expanded decomposition is fast, this is indeed fast. It just remains to show that this is good. This is a good hierarchy. This gives you a good hierarchy. Okay. Yeah.
Is the reason that you couldn't have phi be 1 over polylog because it would explode the number of cuts that you need?
Yes. So actually, if phi is something like 1 over polylog, then the number of levels just maybe increase to log n. And that seems good too. The algorithm is going to still be fast. However, the quality here, you see that it's not good. Yeah. So the reason to set phi to be this big is to control the number of levels to be significantly less than log n. And you see in the analysis here that we need this, that the number of level L is really much smaller than just log n. Good question. Yeah. Yeah.
So we previously already found that using BSE construction we are able to get a good time, and now again we're trying to do this under so many constrained settings, right? So
Wait, sorry. What do you mean? Like we don't have fast algorithm for BSE hierarchy yet. This is like the fast algorithm for it.
okay.
Yeah. So yeah. Like the previous algorithm to build BSE hierarchy is based on this dynamic expanded decomposition where like there are interaction between levels.
Okay.
That's quite slow. Yeah.
Okay.
Yeah. So this is fast. Yeah. Does this answer your question?
Yeah.
Okay. All right. Okay. So now it's really about how to show the expansion guarantee. Okay. So before I go further, let me like talk about some structure. Okay. It's about the contracted cluster and the cluster itself. So let's say that you are at level I. Okay. Look at GI after you contracted I times already, and then you get a cut. This is just the expanded decomposition. Okay. So look at this graph. There is like some component H prime. So you have GI, phi expanded decomposition, so cut it, and this is like one component. First is that observe that like, so this is GI, right? And this is in this boundary here is in CI plus 1. This is like a component after you cut. Now, I just claim that this boundary, when you scale up by boundary link factor beta, plus the edges of H, this edge set is phi prime expanding in H prime. Okay. So why is that? Well, this is really basically almost the definition of boundary link expanded decomposition, right? Because C plus 1 is boundary link expanded decomposition of GI CI plus 1 is expanded decomposition of GI, and it's is beta battery linked. So even if you scale up the battery here by beta factor, and even together with the edges of this guy, the node weighting of edges of this guy. So degree of E of this thing is just the same as, this thing. This is just degree of this graph, the degree node weighting of this graph, H prime. This is phi prime expanding. We just have this. That's a structure that you should keep in mind. By the way, note that when you look at this H prime, this is a graph. This is a component in GI, but GI is a contracted graph, right? So every node in H prime actually corresponds to some induced subgraph in G. So let's consider this H, which is the uncontracted version of H prime. So when you uncontract all supernodes of H prime, you get H. Like this. Just uncontract every supernode. But note one thing, that the boundary of H and H prime will be the same. Just look like the same. It's just going to be the same. And the H set of H prime will look exactly like the separator of H. Right? You see, right? This is just every node of H prime is just a child cluster of H. So the edges in H prime just look like the separator here. And the boundary of H prime is just the same as boundary of H. Good. Okay. And H then is just a level I cluster of the hierarchy. Okay. So H is a component, H prime is a component of Gi minus Ci plus 1, but H is a component of G minus Ci plus 1. So the difference here is a component of G and component of Gi. Yeah. Okay. So just keep this picture in mind. There is, whenever I talk about H prime, there's some corresponding cluster H, just the one that you uncontracting. Yeah. Okay. So now our plan is here. The plan is that how far here should be. Yeah. My plan is this. I'm going to say that if I look at H, which is the level I cluster, okay, which is just a component of G minus Ci plus 1, just from the last picture, last slide, I claim that the boundary of H is expanding. It's going to be alpha to the I expanding. And then the next step is to say that together the boundary here, together with separator, is going to be phi prime times alpha to the I expanding. And if, the analysis here is we don't need it, but it's kind of warm up for the step 2. But once you have step 2, we are done. Once you have step 2, it really just means that for every cluster in our hierarchy, its boundary and its separator is expanding. That's all we need to prove for BSE hierarchy, right? So we're gonna get this thing. h is going to be like a phi prime to the times alpha to the square root log expanding. Like this is like alpha prime times alpha to the square root log BSE hierarchy. And now you see that how big is this thing? This is going to be something like this. So this is where I need that the number of levels is less than log n. You see? Because if the number of level, if like at level I, at the top level, if I can be as big as log n, then this is going to be like a 1 over like polynomial. But if this is just root log n here, then this is like a small. You see? Do you see this now? Like, this is where I like this. Like, if I set, if actually phi prime, I set it to be like 1 over log to the 10, like just some polylog, then we're actually gonna have that the number of level L maybe something like looks like log to the close to, it's going to be actually log n over log n, but it's something close to log n. But then what we're going to get here is then is something like alpha to the log n over log n, but then this thing together is going to be like 1 over n to the 10, like really bad. Yeah. But if we set parameter phi prime like if our phi prime is this instead, is small, then the number of levels is going to be just root log n. So both of these together is still quite big. Okay. So this is like a trick that how to get square root, how to get n to the little one. Yeah, this is like 1 over n to the little one. Okay, good. Okay, so let's start with step 1. Okay. For step 1. I want to show that the battery is expanding. So just now, only thing we need to show is like, given the demand that respect the battery, show how to route it with low congestion. Okay. So I claim that we can route this demand that respect the battery inside H with low congestion. Okay. So the plan is that I just first gonna show how to route in the contracted graph. Okay. And only after that, when I show how to route in the contracted graph, I will try to, it will kind of define how to route between the supernode here. If I can route in contracted graph, now I can see how to route between supernode. And then I just need to show how to route inside each supernode. And that would be done. Okay. Like after the 2 steps, I conclude how to route in H. So I have some demand that respect the battery of H. Let's look at the contracted graph. So I claim that let's say that I have the demand here. Okay. The demand is between the battery of H. I need to route from the green here to green here, from the blue point here to this blue point here. Okay. So this kind of define a way to route in H prime. I just need to route from blue point here to blue point here, green to green here. Okay. Why is it the case that I can route this demand in H with this congestion? Just 1 over alpha. Why is that? What do we know about the boundary of H prime? Any idea? Like why do you think this demand that respect the boundary of H, which is the same thing as respecting the boundary of H prime? Why we can route it with low congestion? Yeah.
We know that the boundary of H prime is alpha expanding in
Yeah. The boundary of H prime.
alpha expanding in H prime, I guess, but it's like the same speed with the same premise.
Exactly. The boundary of H prime is alpha expanding in H prime. Right? So if the boundary is alpha expanding in H prime, then you can route it with congestion 1 over alpha. Why this is true? We only do phi expanded decomposition. Why do we get alpha expansion? Yeah.
Because like to guarantee that the boundary is more expanded.
Exactly. Although we do just phi expanded decomposition, right? Normally, when you route things, you just should get like 1 over phi congestion. But here, this is the demand between boundary. And we do boundary linked expanded decomposition. So the boundary is much more expanding. That's why the congestion is much better. Okay. So the congestion here is just going to be 1 over alpha. So again, we know that the boundary of H prime, even after scaling up by beta, is phi prime expanding in H prime, just because we do expanded decomposition with parameter phi prime. But this implies that boundary of H prime is phi prime multiplied by beta expanding. So this is like, it's just like 1 over log polylog expanding, much better than phi. And this demand here respect the boundary of H, so it respects the same boundary of H prime. So just now we know that, okay, this thing here, you can route D in H prime, sorry, this is H prime. You can route D in H prime with low congestion, like just 1 over polylog congestion. Okay. Right. So now we have a way to route in H prime, which is basically a way to route between supernode of H. Okay. So that basically induce how we should induce the demand how to route inside each supernode. So let's say that I look at each child of HV is like maybe 1 supernode here. Okay. It's like level below H, 1 level below H. So now, what do we know about HV? I know that any demand that respects the boundary of HV is routable in HV with congestion 1 over alpha to the I. How do I know this? I just use induction. Right. Okay. this is our proof that at level I you need this congestion, and I use proof by induction. So the level below I minus 1, I just need this congestion. So I plus 1 minus 1, like 1 over alpha to the I plus 1 minus 1. So it's just this thing. So this is just by induction. Okay. But now, to connect, like when you look at this F prime, the flow in H prime, to connect the flow in the contracted graph inside each supernode. Okay. This demand to connect the flow inside supernode, this is actually 1 over alpha times the battery of HV, respecting demand. Why is that? Because the congestion here is like 1 over alpha, right? So, 1 second. Good, yeah. Like you can look at this demand like from the flow in H prime. It defines like a demand in HV, right? But if the flow in H prime has congestion 1, the demand in HV here would be just like alpha HV. No, sorry, the battery of HV respecting demand. But the congestion in H prime is 1 over alpha. So the demand inside HV here might scale up by 1 over alpha. So this is just a demand that respects the battery of HV multiplied by 1 over alpha. So, I mean, the demand that you try to route here, this demand respect 1 over alpha battery of HV. Okay. But if it's 1 over alpha, if it respects 1 over alpha times the battery of HV, then it means that this is routable with congestion 1 over alpha to the I plus 1. Right? Because if it just respects the battery, you can route with congestion 1 over alpha to the I. But if you scale up by this one, you just have this plus 1 in the congestion. Okay. So it means that inside each of the supernode here, you can route here, connect the flow with congestion 1 over alpha to the I plus 1. So once you connect all these things, you basically successfully route the whole demand. So you basically, by connecting all this flow in each supernode, you route the whole demand D in this with this congestion. Are we good? Okay. So that's the first step. Okay. So you see that the battery actually is quite expanding nicely. Like it's just, the expansion is like alpha to the I, not phi to the I. So much better than phi to the I. Okay. So now I'm just gonna show that when you consider both battery and separator, now is this one. It's this much expanding. And the proof is almost the same. Okay. So if I want that the battery and the separator is expanding, well, just start with the demand D that respect. Let's say D is the demand that respect battery and separator. Maybe D is like this. Okay. You might have some demand between the battery the blue one, the green one, and also the demand that, respect the battery. So it should be maybe, this purple one should be here. Yeah. This orange one should be here. Let's say I want to send flow from the separator to the battery here. So forget this guy. It should be here. The demand is between the orange point here to orange point here. Yeah. So this is like some demand. This is some demand respect the battery and separator. And I want to route this demand D with low congestion. Okay. Good. So the plan is the same. Try to route in the contracted graph first, and then try to route between supernode. Okay, so now I have some demand that respect this. I claim that there is a way to route D in H prime with congestion 1/5 prime. Okay. So this should be easier, but yeah, can you tell me why we can do this again? Yeah.
Because the boundary of H and the separator is phi prime expanding.
Yeah.
H.
Right. So we have that even the boundary of H prime scale up by beta union with separator of H prime, which is actually just H set of H prime. This whole thing is phi prime expanding. So even if I scale this up by beta, it's phi prime expanding. But now, so it means that this thing, union with this thing, is phi prime expanding too. Right. So I can route this one with condition 1/5 prime. Yeah, just because we know that even scale this up by beta, union with the H set is phi prime expanding. Are we good? Why this is true, right? You see that this is true. Because it's just the guarantee of battery leading expanded decomposition. Okay. So, and D respect this thing, but separator of H is just the same as E of H prime. So this demand just respect the battery of H prime and H set of H prime. And this thing is phi prime expanding. Okay. Good. So we get that we can route inside the contracted graph with congestion phi prime, 1/5 prime. So quite worse than before. Before we have 1/alpha, but this is like 1/5 prime. Okay. Now, how to route inside the supernode of H prime. Now it's just the same reasoning, right? Okay. Should forget this again, and the point is starting. The point start here. Okay. We know that once you have a routing in H prime, that induce the demand between each supernode, and inside each supernode here, to route inside the supernode here. This demand is only between the battery of the supernode. Okay. Nothing is inside the supernode. Like there's no demand inside supernode. It's only between battery of the supernode. And from step 1, we know that if the demand is only between battery, the congestion looks like something that depends only on alpha, not phi prime, right? So just from step 1, we have that, okay, maybe I just, yeah. We know that any demand that respect the battery of this supernode HV is routable in HV with this congestion that independent from phi. It's just something that depends on alpha. And then to connect F prime inside HV. This is the demand that like this induces the demand that respect battery of HV scale up by 1 over phi prime. Why 1 over phi prime here? Because the congestion here is like 1 over phi prime. So the demand here just kind of respect the battery, but only up to this factor. But then it means that you can route this demand inside the demand in dV, which is the demand inside HV. You can route it with this congestion. Just this thing scale up by this much. Okay. So just the same, you then connect the flow together, right? Connect everything. And once you connect everything, you get the flow that route the original demand D with this congestion. Okay. Is it good? Yeah. So I think the key insight is that this thing, when you try to route inside supernode, it's just the demand between the battery. Yeah. And the point is that the battery is much more expanding than like the degree node weighting. Yeah. Okay. So we get this one, and so we are done. Okay. Every cluster is such that its battery and its separator is quite expanding. And we choose phi prime to be such that the number of level is just log, square root log, so that this thing together is something like 1 over n to the little 1. Okay, good. So we get this. And you see that this is, it implies the 3 flow specifier with this quality, which is n to the little 1. And at least the algorithm itself is super simple. Just do expanded decomposition, contract, and repeat. The algorithm is extremely simple and fast, but yeah, just takes like polylog max flow. I want to make like the nice thing about this algorithm is simple, and actually because of its simplicity, it has been like implemented in other model of computation, like in the dynamic setting. I and co-author show that you actually can maintain this object in the dynamic graph. Like when you have a graph, you keep inserting, deleting edges. Actually, you can maintain this whole thing dynamically. So you can get this dynamic. And I should say. And once you can do that, it means that you can maintain 3-flow specifier dynamically. Once you have 3-flow specifier, you get dynamic approximate max flow, dynamic min cut, and so on. Okay. But one thing that I will talk more later is that just from, like, in this class, we have been assuming that you can compute max flow in almost linear time. We didn't show yet how to do that. And how people do that is to use this dynamic 3-flow specifier as a subroutine to compute it fast. So this, like the construction that you just saw is the way to build dynamic 3-flow specifier, and that is used as a key subroutine to compute max flow fast. Okay. Yep.
I saw like here we are calling like max flow, so isn't it like circular?
There is a way to build, you see like soon after, like maybe next 3 weeks, how to build this one without calling max flow black box. Also, you can use distributed setting. You get something distributed, like some distributed algorithm. Okay. But the cons is that like the quality is a little one. So if you want to get faster max flow, like it should be M polylog. That would be ideal. It's enough to show how to get dynamic 3-flow specifier with polylog quality and update time. So yeah, that's like really good open problem actually. Okay, let me summarize. What we have seen so far is actually now two construction of BSE hierarchy. One is today, the one based on boundary link expanded decomposition. Just contract and recurse. Yeah. It's good because it's fast, but the quality is bad. The another one based on dynamic expanded decomposition is also nice because this generalized to directed graph and some other expansion notion. I will talk more in this course. Okay. But it's slow, but it has better quality. So what's open is, can we build this with polylog quality and polylog max flow? It could be easy, it could be hard. I don't know. It's just that we are at the frontier right now. Like I didn't think too hard about this too. So that's a good question. Yeah.
Is polylog max flow is like polylog total calls to max flow?
Yeah. Right.
And also, is the max flow algorithm right now? Is it like m times polylog of m?
Not yet. Yeah, like
No,
right now it's something like this.
Oh, a little O1. Okay.
Yeah, little O1. Yeah. But if you find a way to just use this max flow calls, I know many techniques to just not use exact max flow and use approximate max flow. And if you want approximate max flow, you can improve this to just M polylog. Yeah.
So is approximate max flow like a flow that's like within epsilon of the exact value?
Yeah.
And what's the complexity for that?
M polylog.
And polylog of epsilon.
Yeah, like something like M log. Right now log is quite bad, like log to the 10. But something like, for this thing.
Okay.
We will learn an algorithm for computing approximate max flow soon as well in this course. Yeah. Okay, so I will talk, like I recap how to do this thing fast later. But you see that from today, if we assume this thing, which is basically based on what we talked on Friday, then we get really nice way to build BSE hierarchy. Okay, so we we continue on Thursday. Yeah.